Okay, so in this video we're going to look at components and IV characteristics of different components. Probably look at this across two videos. So the first one we're going to look at is essentially why do we look at components the way we look at them. So first of all, what kind of graph to observe IV characteristic do we draw? Well, we draw one that looks a lot like this. And we drew I and V there. Now, in previous videos, I've told you why we do I on the y-axis and V on the x-axis. I'll remind you now, it's because essentially current comes from the idea of the voltage. If you put a PD or an EMF, across a component, what drives that current is the EMF. And so, So what we get here is a situation where this is our independent variable and this is our dependent variable. And just as a rule, generally we'd expect the independent variable to go on the x-axis and the dependent variable, what changes as a result of what we have changed, goes on the y-axis. Now you'll notice here that I've actually gone for a positive and negative graph. So these are positive voltages and currents, and these would be negative voltage and negative current. So why do we look at it from this point of view? Well, we look at it like this because we need to say, well, what happens if we put the current going through the component the other way? Does something change? Now that's not going to be too prevalent when we look at some of the things we look at in this video, but in the next video it's going to be very, very pertinent and it's going to come up as a very important point. So generally we've looked at fixed resistors, and a fixed resistor obeys Ohm's law. Now by obeying Ohm's law, that means we would suggest that current was directly proportional to voltage. So what we'd expect is when we drew our line on this, we would expect this. And hopefully we would have observed that in some of the practicals you would have done with me in class. So we looked at a fixed resistor IV characteristic, and you might have drawn this graph just like that. But the point is that if we then put the current going through the other way, then we would observe the negative voltages and negative currents, and we would observe something like this. Now, obviously that's supposed to be as straight line as possible. I think I've done a pretty good job of that, considering I've drawn that freehand. Now, how do we know this is a fixed resistor? Well, because if we take the gradient anywhere along this line, it's going to be constant. Now, very importantly, if we look at this very specifically and we go, okay, well, how do we know what the resistance is? Well, it's the reciprocal of this gradient. Because remember, this is an IV graph, not a VI graph. It's all well and good just to draw a VI graph and go, oh, VI, and you've got your gradient there, and that gradient would be the resistance of that fixed resistor. In this case, this one right here, that's not the case. We have to do something slightly different. The gradient of this graph would equal 1 over R. Which means to work out what R is, you just do 1 over the gradient would equal R. And so we've got a nice way of looking at that, which also means the steepness of the graph of this graph gives a very strong indication of what the resistance actually is. So say for example, we've got one resistor that looks like the black line that I've already drawn, and we've got another resistor which looks something like this. Okay, it's still obeying Ohm's law, it's still straight line, still directly proportional, and so what we'd expect here is we've got one line which shows one resistance and one line which shows another resistance. So ask yourself, which has the higher resistance? Okay, so if you've worked out which is the higher resistance, well done if you get it right. This red line would be the higher resistance. Why? Because it's less steep on an IV graph. We've got the reciprocal of this gradient will make a very much higher value than the reciprocal of this gradient. I'll remind you again, reciprocal is just 1 over that value. That's all that word means. So, high resistance, lower resistance. Okay, and obviously as it gets steeper and steeper and steeper, you get lower and lower resistance. As it gets less steep towards this side, then you're going to get higher resistance. Please bear in mind that's the opposite on a VI graph. It's the opposite on a VI graph, so please be wary of that. But this is the most common way of showing it because of the way the relationship is actually done experimentally. So let's look at a slightly different component now. Well, a slightly different component could be the filament lamp. Now you're going to be experimenting and hopefully showing this in reality when we come back to class. So how is a filament lamp different? Well, a filament lamp is a non-ohmic resistor. Okay, what I mean by non-ohmic is it doesn't follow Ohm's law. It means that I is not directly proportional to V. So what does a filament lamp graph look like? Well, it looks something like this. Okay, it looks a bit like an S. And yes, that is supposed to be kind of reversed and symmetrical on the other side. So please forgive my drawing. You can be able to see an example of it in the textbook as well, just to confirm any issues you may have with it. So that's what a filament lamp looks like. And again, we're showing what happens when we put the current through the other way as well. So what we've got here is a situation where we've got a changing resistance. How do you know we've got a changing resistance? Well, because it's not a constant gradient. You've got a changing gradient. So you should, from the previous graph, be able to tell me what the resistance is doing as I increase the voltage across my lamp. If it's becoming less and less steep, yep, that's right, you've got it, well done. The resistance is getting higher as I increase the voltage. Okay? So we're getting an increase in resistance for increasing voltage. So this is a non-ohmic resistor. It doesn't follow Ohm's law. Why? Why are we observing this? What does a filament lamp do to make it undergo this change and not be like a fixed resistor with a constant gradient? Well, what's happening here is we've got a situation where if we look deep at the wire, something is changing in the wire to make this happen. You've still got your electrons moving through the wire, and as a result you've got your positive ions as well, which are stationary for the most part. But what you'll notice is that as I drive up the voltage, what we'd normally expect to happen is the current to increase. That's our normal expectation. So as the electrons move through this, they're being forced through at a greater rate. Now that increase of rate causes them to bump into these ions, these positive ions, and via the process of friction generate heat. The more you rub against something, the more heat you're going to generate. So this effectively generates heat. That generation of heat through friction of the rubbing of the electrons against those ions, what happens is that these ions then start to vibrate with lots and lots of energy. They start to vibrate. If they're vibrating, they're becoming more energetic and they're getting in the way more. If they're getting in the way more, what happens to the resistance? Well, the electrons aren't able to flow through as easily, and so the rate of transfer of these electrons slows down. Because they slows down, they have to do more work to get through, which then generates more heat, which then causes them to vibrate more, get in the way more, and so repeats the process. So as a result, that's why we see, for the filament lamp, this effect of heating, causing an increasing resistance as we increase the voltage. So as we increase the voltage, the current would increase, as we'd expect, but because of the heat that's being transferred, causing those ions to vibrate, means that what we have is a situation where they're getting in the way and they are creating more resistance for those electrons to flow through, hence the current, the rate in which the current will increase would drop. Okay? Therefore, more resistance is being created. You may need to watch that video, a couple of times, just to get your head around what's actually happening there. But as long as you understand that increased heat means increased resistance in a normal wire or in a filament lamp, in this case, you're not going to go far wrong. Okay, and that, the effect of that is to see this relationship here, and obviously the reverse, which is the negative version of this graph. So in the next video we'll look at a couple more components, and we'll delve deep into a bit more of why we look at the negative portion of this graph.